In this video, I want to take a look at a couple of results that are related to orthogonality. The first one is one maybe you're not too surprised with, but it says this: if you've got two vectors, u and v, such that they're orthogonal to each other, then the following is true. Take a look at this vector right here. This would be the vector u plus v. Well, the Pythagorean theorem is true, that the length of u plus v squared is the length of u squared plus the length of v squared. You might say, why are we proving this here? Well, the reason we would be proving this here is because the Pythagorean theorem is a two-dimensional theorem. It's about planar things. We happen to be able to see that it works in 3D as well. And again, our textbook does not like to think that we can just assume that geometry works the same in higher dimensions. So it proves it works the same in higher dimensions. Right? So here's the proof of this statement. Take a look at the left-hand side, u plus v squared. I can rewrite that as u plus v. I'm going to stop writing the vector symbols here. Dotted with u plus v. Well, I FOIL that out. I got u dotted with u plus the outsides are u dotted with v. The insides are v dotted with u, but those are the same because you commute, so that's 2 times u dotted with v. And then the last are v dotted with v. So what I have here, I'm going to rewrite this as that length again here. That length squared, u plus v, is the length of u squared, right? Because that's u dotted with itself, plus 2u dotted with v, plus the length of v squared. Now, if I hadn't have assumed that u and v are perpendicular to each other, I would not be able to cancel this out, which I'm about to do. But it would remain here, and this looks a lot like the law of cosines, because this turns into a length of u to length of v times the cosine of the angle, but this is a plus sign instead of a minus sign. It's like, how come this isn't the law of cosines? Well, when I say the length of u times the length of v times the cosine of the angle in between them, this would be not this angle, because this is not the angle in between them, because they're not, the angle in between them would be, if they're both written this way, it would be this angle. Now, when it's 90 degrees, or when it's pi over 2, this angle and that angle are the same, but if this was something like this, with u and v, and then when you moved u over here, or you moved v over whichever way it went, that this angle is not the same as that angle. In fact, it is the supplement of that angle. And so the cosine of this angle and the cosine of that angle would be exactly minus the other one. And so that plus sign would turn into a minus sign. Anyway, this looks like the law of cosines. However, in the special case where u and v are perpendicular to each other, this is 0. And what we end up with is the Pythagorean theorem. The length of the hypotenuse squared is the sum of the squares of the other two sides. All right. Now, the other theorem that we want to look at in this section is one that I know how to get it. I never really remember it because, first of all, I think the way that particularly this book writes it is weird. And if I ever need it, I just look it up just to make sure I've got things right. And this is, part A is the distance from a point to a line. Part B is the distance from a point to a plane. So let's look at part A here. So I'm in the plane somewhere, and I've got a line, and the equation of that line is, and this is where I think this is weird, because I don't hardly ever write the equation of a line that way. I would write it as ax plus by equals c. And so because I write it this way, my c is the negative of their c. And so where they have a plus c in here, I always end up with a minus c. because my c is on the other side of the equation. This is one reason why I don't try to remember this one, because I know it's just weird. But here's the idea. The proof is in the book, and I'll let you read that in the book. But the idea is, if I've got this equation, whether I write it this way or the way the book does, I know that the normal vector is the vector AB. Okay. And if I had a point on the line, let's call that xy, the point xy on the line would satisfy this equation. Now, they're saying take a point that's not necessarily on the line, call it x0, y0, and the question is, how far away from the line is it? Well, when you say how far away from the line, you actually mean perpendicular distance. Well, the perpendicular distance could be found in the following way. Think about the vector that goes from xy out to x0, y0, and project that onto the normal vector. So I want to project onto the vector AB the vector of these, which would be x0, y0 minus xy. So project this vector onto the normal vector, and that's what I get. Well, the projection is going to be a dot product of this with that, divided by the dot product of this with itself, right? Oh, I'm sorry. I'm not doing the projection. I'm doing the scalar projection. I was doing the formula for vector projection there, but really I want the scalar projection. So the scalar projection should just be the dot product of these two things divided by the length of the thing you're projecting onto. Well, notice the denominator here is the length of that normal vector. And the numerator is going to be the dot product of this with this, which means you're going to dot it with the first one, you're going to dot it with the second one, and subtract. So the dot product with the first one is this stuff right here, and the dot product of the second one is ax plus by. Well, ax plus by is equal to c, right? Because that point is on the line. And so this part right here, when you dot it with the normal vector, turns into that c. Now, because the book would have the c written on this side, they have a plus c there. Me writing the c on the other side, I end up with a minus c right there. But either way, it works. The step-by-step details are in the book. What I want to point out is that these formulas, although they look kind of big, are really just the projection of one vector onto the normal vector, so you can calculate that distance, that perpendicular distance. Okay. Likewise, in R3 with a plane, it's the same calculation, but the equation isn't just ax plus by equals c, it's ax plus by plus cz equals d. And again, they don't write it that way. They put the d on this side, which I never do. But anyway, I would have a minus d where they have a plus d. Anyway, there's a couple of geometric results that we use projections to calculate.